Picture computers solving problems in seconds that would take today's supercomputers millions of years. From AI, medicine and cryptography to climate, finance, and materials science, quantum technology will redefine the future. Today, you'll understand quantum computing, how it works, what it can do, its limitations, its challenges, and why it might change the world forever. Classical computers think in bits, 0 or 1. Quantum computers, they think in qubits, 0, 1, or both at once. Superposition means they explore multiple states simultaneously. And then comes entanglement, qubits linked so tightly that a change in one instantly affects the other, even across galaxies. Quantum gates, Hadamard, Poly-X, CNOT, Toffoli, control these states, creating logic circuits unlike anything classical. Shor's algorithm breaks massive numbers, threatening modern encryption. Grover's algorithm searches data exponentially faster. But there's a problem, decoherence. Qubits collapse under noise. Error correction is essential. Qubits come in many flavors, superconducting circuits, trapped ions, photons, topological qubits, each racing to unlock practical quantum power. Classical computers crawl lane by lane. Quantum computers teleport across all lanes simultaneously. That's the difference. Sequential versus parallel. Deterministic versus probabilistic. Ordinary versus quantum. Let's zoom in on the star of the show, the qubit. Unlike a boring classical bit that's stuck being a 0 or a 1, a qubit can be 0, 1, or both at the same time, thanks to a magical property called superposition. Think of it like a coin spinning in the air, not heads, not tails, but somehow, both. Now, here's where things get wild, entanglement. Two qubits can be mysteriously linked so that what happens to one, instantly affects the other, even if they're light years apart. Einstein called it spooky action at a distance. Scientists call it, our secret weapon. With superposition and entanglement together, quantum computers can explore countless possibilities all at once. To control them, we use quantum gates. They rotate, flip, twist, and tangle qubits into the patterns we want. Hadamard creates superpositions. Poly-X flips. CNOT entangles. Toffoli builds logic blocks. Put them together, and you've got a quantum circuit, a machine that doesn't just compute, it dances with probabilities, collapsing into answers when measured. Fragile, delicate, brilliant. That's the qubit, the strangest computer part humanity has ever built. Imagine this, the world's strongest safe. Billions of numbers guarded, and no classical computer could break in, not in the lifetime of the universe. Enter Shor's algorithm, a thief so clever, it slices through those numbers like butter. Suddenly, every bank, every secret, every password, vulnerable. And then comes Grover's algorithm, the world's fastest detective. Instead of searching line by line, clue by clue, it leaps across possibilities, cutting the work in half, then half again, until the answer just pops out. How do they do it? With quantum gates, the choreographers of the quantum dance. The Hadamard spins a coin into infinite flips. The Poly-X, a rebellious switch, turning 0 into 1. The CNOT, the ultimate tag team move, one qubit drags the other into entanglement. And the Toffoli, a mastermind gate, building complex strategies out of simple moves. Together, these gates don't just compute. They unleash algorithms that can rewrite the rules of reality itself. 2019, the world held its breath. Google's quantum computer, Sycamore, performed a calculation in 200 seconds. The same task would have taken the most powerful supercomputer on Earth 10,000 years. This was the birth of quantum supremacy, the first time a quantum machine outperformed every classical rival. Of course, critics argued, it's a party trick, no real-world use. But history reminds us, the Wright brothers' first flight didn't carry passengers either. It proved the skies could be conquered. Quantum supremacy isn't about today's problem. It's about tomorrow's revolution, when every bank, hospital, lab, and government will face a choice, adapt, or be left behind. Quantum computing isn't just math. It's medicine, it's money, it's survival. In healthcare, quantum simulations could design new drugs in weeks instead of decades, curing diseases before they spread. Imagine testing billions of molecules inside a quantum lab, all at once. In finance, quantum algorithms could detect patterns invisible to Wall Street's brightest minds, unlocking profits or exposing hidden risks. For climate, they could model Earth's atmosphere with terrifying precision, predicting storms, floods, even global warming decades ahead. And in cybersecurity, today's encryption would fall. Secrets, bank accounts, entire governments, wide open. But quantum can also defend, creating unbreakable codes through quantum encryption, messages so secure, even the universe can't crack them. Medicine, finance, climate, security. Quantum isn't just about speed, it's about reshaping the future of humanity. So now let's see the challenges. Why quantum computing is hard. Every hero's journey has a villain. For quantum computers, that villain is fragility. Qubits are delicate, so delicate that a single vibration, a stray photon, or even background radiation, can erase their state. This is called decoherence, the collapse of quantum magic into classical boredom. Imagine juggling 10 flaming torches in a hurricane. That's what keeping qubits stable feels like. Noise creeps in, errors multiply, and unlike your laptop, you can't just restart. A single mistake can ripple through the entire calculation, turning brilliance into gibberish. So researchers fight back with quantum error correction, layering qubits on top of qubits, creating armies of backups just to keep one logical qubit alive. Today's machines may boast hundreds of qubits, but once you add error correction, that power shrinks dramatically. It's a reminder, raw numbers don't mean true strength. Stability is the real battleground. And yet, humanity doesn't give up. From superconducting circuits chilled near absolute zero, to ions trapped by lasers, to photons racing through crystals, every approach is a gamble. One of them may hold the key to taming quantum's chaos. The global race, who will win? Quantum isn't just science. It's a weapon, a currency, a crown jewel in the new technological arms race. The United States pours billions into quantum labs, Google, IBM, Microsoft, racing ahead with superconducting circuits and hybrid quantum classical systems. China answers with national pride and staggering investment, building some of the world's most advanced quantum communication satellites, aiming for quantum-secure networks that no hacker can touch. Europe, they unite under the quantum flagship, funneling resources into research hubs, betting on long-term dominance. And startups, scrappy dreamers in garages and small labs, dare to compete with giants. Companies like Rigetti, IonQ, PsiQuantum, armed not with billions, but with bold ideas. Governments know, the first to harness quantum may own the future of encryption, finance, even artificial intelligence. It's no longer about building the fastest computer. It's about building the most useful one before someone else does. This is the global quantum race. A marathon disguised as a sprint, where the finish line could redefine power itself. Quantum plus AI. Two revolutions walk into the same lab, AI and quantum. What happens next? AI learns patterns. Quantum explores possibilities. Together, they don't just predict the future, they manufacture it. Quantum accelerates model training, turbocharges optimization, and searches gigantic parameter spaces in a single breath. Imagine giving your AI a jetpack, then teleportation. But power cuts both ways. Better models mean better scams, deeper deepfakes, faster cyber attacks. So we pair it with quantum-safe security, guardrails, audits, and human oversight. Power is neutral. Purpose decides the story. Quantum plus AI won't replace people. It amplifies them, turning good ideas into breakthroughs. Your secrets rest behind math. Today's locks, RSA, ECC, solid, unbreakable, for classical machines. Then Shor's algorithm kicks the door. Keys that should last centuries, gone. Enter post-quantum cryptography, new locks designed to survive the storm, lattices, hashes, codes. Migrate early, rotate keys. Inventory every place encryption lives, servers, clouds, phones, backups. Because adversaries are harvesting data now to decrypt later. Offense evolves. Defense adapts. The winners will be the ones who planned before the sirens. For ways to build a qubit. For contenders. One crown. Superconducting circuits. Chips chilled near absolute zero. Fast gates. Industry momentum. But noise is a constant shadow. Trapped ions. Atoms levitating in laser light. Beautiful coherence. Slower gates. Exquisite control. Photonic qubits. Particles of light racing through waveguides. Room temperature promise. Tough to interact. Brilliant for networking. Topological qubits. Exotic states designed to ignore noise. Hard to realize, but if cracked. Stability like nothing else. Different tools for different quests. Chemistry, optimization, cryptography, networking. There may not be one winner, just the right machine for the right mission. Error correction. From noisy to useful. Noisy qubits are musical geniuses with stage fright. Error correction is the entourage. We bundle many physical qubits into one logical qubit. We detect mistakes without peeking at the music. Surface codes. Repetition codes. Magic state factories for universal logic. The price? Overhead. Dozens, maybe thousands, of physical qubits per logical one. But thresholds rise. Hardware improves. Compilers get smarter. Every month the gap shrinks. From noisy toys to reliable instruments. The quantum internet. Why send entanglement? What if we don't just send bits? We send entanglement. QKD shares keys with physics-level security. Teleportation moves quantum states without moving matter. Repeaters extend entanglement across continents. Secure finance. Protected government links. Quantum cloud services chaining specialized processors. A web where trust isn't assumed, it's proven by nature. How to join the quantum era. You don't need a PhD to enter the frontier. just momentum. Choose a lane: algorithms, hardware, control, compilers, applications, security, design and visualization. Learn linear algebra, complex numbers, basic quantum gates. Practice on open source SDKs, build tiny demos, Grover on 4 qubits, VQE for a toy molecule. Pair quantum skills with a domain: chemistry, finance, logistics, cybersecurity. The future belongs to hybrids, people who bridge worlds. Myths versus reality. Myth: quantum replaces classical. Reality: they become teammates. Myth: quantum can do everything. Reality: only certain problems explode with speed. Myth: encryption is doomed today. Reality: plan the migration, win tomorrow. Ethics and impact. Every great tool is a mirror. Quantum will reflect who we are. Open science versus strategic secrecy. Break encryption versus protect privacy. Automate jobs versus create new ones. Policies, standards, transparency, engineered with the tech, not after it. If we build with wisdom, the future gets wider, fairer, brighter. 3 futures. Slow burn, steady progress, niche wins first. Quantum spring, error correction cracks wide open, apps explode. Leapfrog, quantum networking outpaces computing, security leads. Which future arrives depends on us: investment, education, collaboration. From fragile qubits to world-shaping machines, this is the story we're writing now. Whether you become a builder, a defender, or a translator, welcome to the quantum era. Subscribe to TechBeyond. The future isn't out there. It's in your hands.